All right, hi guys. So I was asked to work through some of the examples for like two-dimensional collisions, or I wrote it on here as two-dimensional momentum. So for this lesson, if you look at the notes, it specifically says we're gonna go to a limit with this lesson. So it says in the notes online, AP Physics 1 only requires students to set up the equations properly and be able to discuss how changing the mass, speed, or angle of the problem affects the other quantities. So the full numerical solution isn't exactly necessary, but you should be able to set up these formulas. And a lot of this is just based in your understanding of X and Y components in general, which we've done this a lot of times where we break it down, we use cosine and sine to set up our formulas here. So what we're going to do is I'm going to look at this problem with you guys and try to really simplify it and kind of shorten it a bit because I don't want to overcomplicate the process for you. The main point of this problem here, so we have a bowling ball and a bowling pin. So the bowling ball is M1, hits the bowling pin, and after the fact, the two split off going two separate ways. And the main point is that in both the X and Y direction, we should have the same momentum in total in the beginning and the end. So in the X direction for this first system right here, you can see the bowling pin's not moving. The bowling ball has a momentum of 20 kilograms meters per second. And then the bowling pin has zero momentum in either direction, and the bowling ball has no momentum up or down. So in general, we have just no motion in that y direction, which leads us to understand that the initial momentum in the y direction is zero. So that's before, and then after the fact, we should be able to say that the initial total momentum in the x direction is equal to after. And same for y. So that's what that apostrophe means, like momentum after. So the total. And when we're breaking this down for the two objects, I'm going to break it into different colors here. So, I don't know, I'll use pink. So, for the first object, we only have one value, which is 20 kilograms meters per second over here. And then after the fact, it tells us a little bit more about motion. So right away, I know I'm given an angled vector, and I just don't work with angles, right? I don't work with vectors that are angled. I work with their x and y components. So I'm going to have to break that down anyway. So I'm going to set up a little formula to do that. So this is object 1. After the fact, I need to figure out its x and its y components. And I got to add my apostrophes here to say this is after. So I'm going to turn that 12 kilogram meters per second vector into a little triangle over here to make it a little more visually understandable. And I have theta right here, and I'm trying to solve for the y component and the x component. So really, this y component, if I was going to draw a symbol out for it, this is the momentum of the first object in the y direction after collision. And then down here, this is the momentum of the first object in the x direction after the collision. So that's what each of those symbols represents. So if I was trying to create a formula for these, I would use the angle theta, which is actually 60 degrees, and the hypotenuse of 12 kilograms meters per second to create a formula. So the x component is adjacent to the angle. So this will be the one where we do hypotenuse cosine of theta. And this is something we've done before where we break it into x and y. And then over here, because we're opposite for the y component, we do 12 sine of theta. So when you plug those into your calculator, you should get 12 sine of 60 is 10.4, and then up here is 14. So I know that my total in the x direction still has to be 20 kilograms meters per second. And my total in the y direction still has to be 0, like my net, meaning adding them all up. So I'm going to create a formula for the x component and y component of my second object here. So the momentum of the second object in the x direction after collision is equal to what? Well, I know that I have to have a total in the x direction of 20. So that is my momentum after the fact in the x direction, my total momentum. And I also know another component is I have my piece of that, which is 14. All in all, we're just trying to find what adds up to 20 from 14. But they want us to create a little formula. So our formula for that would be P total in the x direction after the collision minus whatever other pieces we have. So in this case, we have the x component of the bowling ball, which is P1x after the collision. And what that really does is we just got to do 20 minus 14, which is 6. And then the same thing goes for the y direction. So we'll say to figure out the y direction, and we're turning this, kind of creating the components of turning this vector going downward into its own triangle here. So this is P2y theta, P2x theta. So we're really figuring out like 2 out of the 3 legs of the bowling pin's momentum after. So then we would say that this is equal to the total momentum minus whatever y components we have. And the total momentum is 0. The y component we have is 10.4. So we should have negative 10.4. Don't mind me not putting my units, but we should have negative 10.4 as our y component. And this makes sense because our y component leg for the bowling ball is going downward. So now we basically just need to figure out the number and angle of this leg right here, which we've done time and time again. So to do that, I'm going to use the 2 legs, which I now know I can label are 6 and negative 10.14. And we're going to figure out the magnitude of this angle here. So we can use a squared plus b squared equals c squared, Pythagorean theorem, to figure out the magnitude. So c equals 6 squared plus, I'm just going to put 10.4 because it's going to square away anyway. Okay, well, we could put negative, but it's going to get rid of it. So solving for that component, we get 17.4 kilograms meters per second. And then in our notes, it has us solve using tangent. So we'll just kind of follow that process. And to get the angle, it's opposite over hypotenuse. So tangent of theta equals P2y theta over P2 x theta. And obviously we got to do tan inverse to really solve here. So you have negative 10.4 over 6. And when you put that in your calculator, you'll get about negative 36.6 degrees. And that makes sense because we're headed downward. So we have a magnitude, and an angle. And what we can really gather from this is if we have an object that goes upward and our initial momentum in the y direction was 0, then we need an object going downward in order to cancel that out and bring that total momentum in the y direction back to 0. So that's example 1. All right, so now let's look at example 2. Again, we're following along with this idea of like momentum needs to be conserved in both the x component and y component of the system. So this, we have two objects collide and stick together. They're coming at an angle, pretty much just like at an intersection, and they're going to stick together and travel together. So we want to figure out what the angle is that they're going to move at after the collision. And you can see there's no numbers here, so this is more so what they're going to want us to solve for is collisions with no actual numbers involved when it comes to two-dimensional collisions. And you can see we skipped over one problem just for time's sake, so you don't have to worry about those slides. We're just going to focus on this one. So what's nice about this problem, and it doesn't look nice to begin with, but it actually is the fact that in the beginning, both of these objects are moving at completely different directions. So I say it doesn't look nice because it sounds like it's going to be complicated, but it makes it very simple for us to determine what our total momentum in the x direction should be because we only have one momentum, that is P1. And then in the y direction, our total momentum is P2. There's no y component here, there's no x component here. So just like we did before, I'm just identifying any givens I can. After the fact, that has to also still be true. So after the fact, in the x direction, we should still have P1. And in the y direction, the momentum should still be equal to P2, whatever P2 is. We don't have a number for it. So with that being said, when we want to try to solve for an angle here, we're going to label this triangle with P2 here and P1 here. And it looks like in our notes they label these PY and PX. It doesn't particularly matter, but the main point is understanding how to get that angle. So if I'm trying to solve for this angle, we don't know what our magnitude of our hypotenuse is at all. We're going to use our earliest known givens. In this case, that's the momentum in the y direction and the x direction. And we're going to plug them into one of our trig formulas. So to figure it out, we have two legs, right? We don't have the hypotenuse, so we have to use tangent. Tangent of theta equals, obviously, opposite over adjacent. So tangent of theta equals P2 over P1. And then if we were actually like rearranging this to solve for theta itself, we have tan inverse of those two values. And that would be an acceptable formula to set up to solve for this on the AP test. All right, so example 3 here, you have an explosion of an object. Think of it like a firework. And two of the components go straight up and straight to the right. And then the third component goes downward. And we're trying to figure out what is the momentum of this third component here. And when it just says momentum, they're not asking for just the x or y. They're asking for you to kind of create a formula for this angled component here. So same concept as the other two. We know that the momentum in the x direction and the y direction have to stay the same. So after the fact, they should be the same. We also know that if this is an explosion of something like a firework, there is no momentum to begin with. Like the momentum, net momentum is 0. So that should still be the same in the end. So just looking at this diagram here, that means that if all of the first piece's momentum is in the x direction, this component right here has to be able to cancel that out in order for this to be equal to 0. So these must be equal in magnitude. So this is also equal to P1 after the collision's magnitude. And the same thing goes for the y direction. After the fact, the second object or second piece goes straight up in the y direction. So this component down here has to be equal in magnitude to that size in order for them to cancel out. So this is the negative of P2 going upward, and this is the negative of P1 going downward. So if these were numbers, you'd add them up, they'd add up to 0. So let's try to write out a formula to solve for P3 and the angle of P3. So to solve for the leg itself, we'd use Pythagorean theorem. So we would say, like we've done before, C, or the theta, is equal to a squared plus b squared. And we could say that P13, which is the one we're trying to solve for, is equal to the square root of negative P1 squared plus negative P2 squared. Kind of set that backwards, but there's a bunch of different ways to write this answer. It just has to show that the magnitude of the x components have to cancel out and the magnitude of the y components have to cancel out. So this will be like my formula for solving for that leg, and that's all they want you to do. They want you to give them a formula. And then to get theta, I'm just going to use tangent like we did before. And to find this theta right here, my opposite would be P1 over P2. And if I'm really rearranging that to actually get theta alone, it would look like this. I'm going to have to put a slash in there. And that would be my answer. So I think in the slides it shows you a couple different options possibly. Let's see. Yeah, it shows you a lot of equivalencies. All of these would be okay options. Let's see. Yeah, they mentioned the x and y components, but these would all still be like viable options because we know that the second object's momentum is all in the y direction and the first object's momentum is all in the x direction. So they set these up in the slides to show you like all the different ways you could rewrite this, but these are both viable answers. This final question here I'm going to run through. I'm actually going to do it without any math involved, just to show you how you guys can understand these conceptually, like just from a viewpoint, and see how there's ways to simplify it. So you have an object, let's see, it says a golf ball collides elastically with a rigid wall that does not move. Ignore any impact on the internal energy of the wall. So we don't have to care about the wall. The angle of incidence requires the rebound angle, or the angle of incidence equals the rebound angle of the golf ball. Given the constraints, what can be said about the momenta in the x and y direction? All right, so basically it's saying that these are two perfectly identical triangles, just flipped. So those angles are the same. Obviously, one angle is below the horizon, one is above the horizon, but they're the same. So it's asking us what changes in the x and y direction, if anything. So just looking at the diagram, the y direction, you can tell from the diagram these are the same magnitude and they're also in the same direction. So the y direction no change. And then in the x direction, you can tell from the diagram that this lower component here is pointed towards the right, and the upper component is pointed towards the left. Same magnitude. So if you were to describe this, and obviously you would write this a lot more in depth on the AP test, but in the y direction, magnitude is the same, but the direction is the opposite. And that's all they're really asking you guys to understand about these diagrams here. So you will say that in the y direction there is no change, but in the x direction there is a change. Hopefully that kind of makes these a little less intimidating for you guys, because it shouldn't be. That's really what they're asking us to understand. When I talk about conceptually, this is what I mean in terms of what you should be able to gather from the diagram conceptually and explain to an AP reader.